Okay, now we will look at geometric random variables. These are similar to a Poisson random variable in the fact that our x, our distribution is infinite, and as x gets larger, the probability gets infinitely smaller. The sum is still equivalent to 1. So the two differences: one, that the probability just doesn't fit a Poisson distribution. The major thing is, though, in each of these three word problem examples, we'll show that the outcomes have two choices. Okay, without reading through these, we could quickly see two competing companies. Okay, you either get a red or you get a blue. The probability of an infection: the person is either infected, 5%, or they are not infected. Okay, person shooting at a target: they either will hit or they will miss, right? You flip a coin, you get a heads or a tails. Those all follow geometric distributions. And with that, we have these formulas to the upper right in green again. Okay, so if x is a geometric random variable with parameter p equals 0.9, so the probability of something happening here is 0.9. We want to first find these probabilities, p naught all the way up to p5, and then make a histogram. Right, so again, following the formula, p sub 0, or p naught, is the probability 0.9 to the n, so to the 0, multiplied by 1 minus the probability 0.9. Okay, so anything to the 0 is 1, so we get 1 times 1 minus 0.9 is 0.1, so 1 times 0.1 is 0.1. Right? P1 is 0.9 to the 1 multiplied by 1 minus 0.9. So 0.9 multiplied by 0.1 is 0.09. Notice that as we go, what's changing? We have this extra p, right? The extra 0.9. So the 1/10 of 1 minus 0.9, the 0.1, right? That's not changing. So all in all, what we can do is take this previous result, if I'm doing all of them, and just multiply it by the p, which is 0.9. So here we get a 0.081, p3. I'm just going to squeeze these in. Multiply that by 0.9. We get a 0.0729, p4. We get 0.06561, and so forth. Okay. Make a histogram. So p naught, p naught we get 0.1. Right now, a histogram, we don't we're not going to graph something. I'm going to just start 0 here, right? A histogram and 0.1, so we'll just say 0.1 is here, 1/10, looks like this. Okay, they're discrete, right? It's not continuous. At 0, p0, I get that value. At p1, we get 0.09. So that's pretty close to that 0.1. And then for 2, what do we get? 0.081. So again, it's decreasing each time, right? So I don't need to keep going, fill that in. You get the idea. As we tend to infinity, as we get larger and larger, this thing, it's never going to be 0, but it's going to be close enough to 0 to where the sum of that infinite series, all the probabilities, will in fact give us 1. Alrighty. Let's look at this next one. So we have two competing taxi cab companies, red and blue. They mix with a random manner. There are 3 times as many red taxis as there are blue taxis. Suppose you stand on the downtown street corner and count the number of X of red taxis. So that's important. They're telling us X is the number of red taxis before the first blue taxi appears. Part A, find the formula. All right. So Pn equals the probability of n. So the probability that's going to be a red. Well, we said there were 3 times as many, right? So another way of looking at that is if there were 4, 3/4 of those are red, right? For every 3 reds, we have 1 blue. So the probability of seeing the red is 3/4 to the n multiplied by 1 minus p, which that's always just going to be the other probability. If one probability is 3/4, the other is 1/4. But I'm going to go in and write it out. Just follow the formula. So we get 3/4 to the n multiplied by 1/4. Okay, that's our formula. I'm going to show this a different way in the next example, but I mean similar, but different way of thinking of it. All right. So B. What's the probability? I can just shorthanded this. Observing at least 3 red taxis before the first blue. Well, because X is the number of red, right, we're then asking the probability that X is greater or equal to 3. If I want to observe at least 3 red, then X is the number of reds, right? X is greater or equal to 3. Well, that would take, I need the probability of 3 plus probability of 4 plus probability of 5, right? And do that forever. Or the complement is what we call it. Remember the sum of 2 probabilities complements sums to 1. So therefore this would be equivalent to just saying, right, find all the probabilities of X less than or equal to 2, so 0, 1, and 2, and subtract that from 1. So therefore we could do 1 minus probability of 2 minus probability of 1 minus probability of 0. Right? If I take out those 3 cases from 1, then I'd have the probability of all the rest. Now looking at that formula above, 1 minus, so P2 is 3/4 squared times 1/4. Minus P1 is 3/4 times 1/4. Minus P0 is 3/4 to the 0, which is 1 times 1/4. I'm using some factoring, I guess. Now we could just plug it in a calculator, really, but I'm going to factor out that 1/4. Then I would have 3/4 squared, right? That's 9/16 minus 1/4, and then minus 3/4 to the 0 was 1, so minus 1. If we get an LCD, we could do 16, right? So this would be 4/16. Ooh, that came out big. So that would be 4/16, and this would be 16/16. So 9 minus 4 minus 16 is negative 11. 9 minus 5. Yeah. So negative 11/16. Oh, geez. It's acting weird. Okay, let's erase that. You know what? You could just plug that in a calculator, really. Right? My thing's being weird. And we care about that more anyways. About 0.4219. That's the probability that you'd observe at least 3 reds before the first blue. I want to throw in one more thing here. So what is E of X in this case, right? What is the expected value I think it would make sense that we would expect, like, how many reds would you expect to see? That we'd probably expect to see 3, but let's verify that. So e of x is p over 1 minus p. So 3/4, right, is p, the probability of seeing a red, over 1 minus p, which is 1/4. Like I said, these two probabilities always add up to 1. If that's p, that's 1 minus p. So 3/4 divided by 1/4, we could reciprocal and multiply, or just cancel the 4s. We'd get 3 over 1, which is 3. So the expected value in this example, the average number of red taxis prior to seeing the first blue would be 3, which kind of makes sense. All right. Next one, this probability of an infection. Suppose a large number of persons become infected by a particular strain of whatever that's called, some sort of food poisoning at a fast food restaurant, and the germ usually produces a certain symptom in 5% of the persons infected. Okay, so 95%, right, wouldn't even know, or they don't get a symptom. So what is the probability that when customers are examined, the first person to have the symptom is the 5th customer examined? Okay. So here's how I like to think of it. That would mean the first 4 are good, right? No symptoms. Non-symptomatic. I don't know how to spell it, so we'll just leave it like that. But then the 5th has symptoms. So if I observe these at random, just because the first person is non-symptomatic, wouldn't mean, right, like person 1, 2, 3, 4, 5. This person has no bearing on the second person. The second person has no bearing on the third. These are all called independent events. It's an equal probability that with this 5% that they are infected or not. So if the first 4 are non-symptomatic, that would mean I have a 0.95 chance, right, for all 4 of these. So 0.95 times 0.95 times 0.95 4 times, or 0.95 to the 4th. But then that 5th, because that's what the question is posing, is symptomatic, there's a 5% chance. Now if you compare this to the formula the way I just explained it, p to the n, right, 0.95 to the 4th, p to the n, multiplied by 1 minus p, multiplied by 1 minus 0.95, 0.05. The reason I like thinking of this a little bit better is because this 5th person examined, right, if I just read it and tried to follow the formula, I would have probably done, either 0.95 to the 5th or 0.05 to the 5th. But you could tell here both of those are incorrect. So sometimes it's better thinking of the actual event occurring like I did here. All right. Anyways, plug that in a calculator because I can't do 0.95 to the 4th in my head. And you get 0.04073. All right. Last one here. Person shooting at a target has 5 successive hits and then a miss. So if we call x the probability of success, so the probability of success, 5 in a row, just like I did in the previous example, right? Those are all your probability of hitting, 5 in a row, so to the 5th power, times the 1 miss. The next shot is a miss. So using some calculus, take the first and second derivatives to determine the value of x for which the probability has its max value. So max value means the first derivative is 0, right? And a max, the second derivative, would have to be negative because we need it to be concave down. So I need to find my critical points where the first derivative is 0, second derivative is negative. So if we go y equals this here, x to the fifth, I'm going to go ahead and distribute x to the fifth minus x to the sixth. I don't really feel like using product rule, although it wouldn't have been bad. Okay, then its derivative is 5x to the fourth minus 6x to the fifth. Set that equal to 0, right? Find the critical points. That's going to bother me here. Okay, find the critical points. We factor on x to the fourth, and we get 5 minus 6x. So x could be 0, or 5 equals 6x, so x is 6 over 5. Oh, 5 over 6. Right, 5, and then I divide 6 on both sides. I was looking at that, I'm like, 6 over 5 probability, that doesn't make sense. It's over 1. Okay, so more than likely, you know, that is going to be a max. The probability of the success is 5 out of 6, which kind of makes sense because right, they just said 5 successive and then a miss, so 5 out of 6 would hit. But let's verify it. We need to know, does the second derivative, is it negative at that point? So we'll look at this and do second derivative. That's 20x to the third minus 30x to the fourth. I need to plug in 5, 6. Right, plug in, substitute 5, 6. And I'm going to go in and factor that really quick, actually. If I do 10x to the third, I'd get 2 minus 3x. Okay, why did I do that? Because now when I look at 5, 6, right, I know that this is positive. And when I plug in 5, 6 here, that would be 3 times 2 minus 3 times 5, 6. So I cancel, and I'd get a 2 in the denominator. So 2 minus 5 halves, which is 2.5, right? 2 minus 2.5 is a negative. So positive times a negative is a negative, so that is less than 0, like we expected, which means this value of 5, 6 is in fact a max. I didn't mean to ignore 0, but it really just doesn't make sense, right? The probability of a hit is 0%. That one just, we could tell without even testing anything. So probability of the success is x equals 5 over 6.